Space isn't just emptiness. It's a vast stage where matter dances, light travels, and gravity writes the script. Between every star and atom lies a silent geometry, invisible yet full of motion. Even nothing in space hums with energy, vibrating with virtual particles that flicker in and out of existence. Space is not absence. It's the canvas on which the universe paints itself, endlessly expanding, endlessly mysterious. Chapter 3. How did time begin? Time began with the Big Bang, not just space exploding outward, but time itself starting to tick. Before that, there was no before. Every atom, every heartbeat since has been part of that same unfolding clock. Time isn't just something we feel, it's woven into the universe. Einstein showed us that time bends with gravity. The deeper the curve of space, the slower time flows. Even time can stretch. Chapter 4. Can time stop? Imagine standing at the edge of a black hole. Gravity pulls so hard that time itself slows to a crawl. From far away, you'd seem frozen, a statue on the edge of eternity. In that moment, time merely stops. But for you, it still flows normally. That's relativity. Time is personal, shaped by where you are and how you move. It never stops, but it can nearly pause forever. Chapter 5. How big is the universe? The observable universe spans about 93 billion light-years. But that's just what we can see. Beyond it, more galaxies, more space, maybe infinite. Light from distant stars takes billions of years to reach us. So when we look up, we're peering into the past. The further we gaze, the younger the universe becomes, like rewinding a cosmic movie. Somewhere, right now, new stars are being born from ancient light. Chapter 6. What is a black hole? A black hole is where gravity wins. It crushes matter into a single point of infinite density, a singularity. Around it lies the event horizon, a one-way door where light itself can't escape. Yet black holes aren't entirely dark. Hawking radiation slowly leaks from them, whispering the story of what fell inside. They are both destroyers and keepers of cosmic memory, the ultimate paradox in physics. Chapter 7. Do wormholes exist? In theory, wormholes exist. They're shortcuts through space-time, tunnels connecting two distant points. Einstein's equations allow them, but stability is the problem. They'd collapse instantly without exotic matter holding them open. If we could master that, space travel could become timeless, a step, not a voyage. For now, they remain beautiful math and science, fiction's favorite doorways through the universe. Chapter 8. What is dark matter? Everything we see, stars, planets, you, makes up less than 5% of the universe. The rest is invisible. Dark matter doesn't shine or absorb light, but its gravity shapes galaxies. Without it, stars would drift apart. We don't know what it's made of, but it's there, a silent skeleton holding the cosmos together. It's not a mystery of nothingness, but of something unseen, yet undeniably real. Chapter 9. What is dark energy? If dark matter holds the universe together, dark energy pushes it apart. It's the unknown force driving cosmic acceleration, stretching galaxies faster and faster. Discovered by accident, it rewrote our understanding of fate. Will the universe expand forever, growing cold and empty? Or will dark energy shift again, folding space back into itself? We don't know, but the universe isn't slowing down. It's racing into the future. Chapter 10. Why does time move forward? We remember the past, not the future, because of entropy, the law that everything drifts from order to chaos. An egg can crack, but never uncrack. Time's arrow points the same way. It's not just memory, it's physics. Yet in quantum mechanics, time doesn't truly have a direction. On that scale, particles don't care about before or after. Maybe time's flow is just how we experience change. Chapter 11. What is gravity really? Gravity isn't a force pulling down. It's the curve of space itself. Massive objects like stars or planets bend the space around them, and everything nearby simply follows that curve. You're not being pulled to Earth. You're falling along the shape of space it creates. Einstein replaced Newton's invisible hand with geometry, turning gravity from a mystery into a map. We don't fall through space. We fall through space-time. Chapter 12. Can we escape gravity? To escape Earth's gravity, you must move faster than 11.2 kilometers per second. That's escape velocity. Rockets don't break free instantly. They climb, fighting resistance until gravity weakens. But even when you reach orbit, gravity never disappears. Astronauts float because they're falling forever, curving around the planet. Gravity is not something you escape. It's something you dance with at the right speed and angle. Chapter 13. What is the speed of light? Light moves at 299,792 kilometers per second. Nothing with mass can go faster. It's the universe's ultimate speed limit. But light doesn't just move fast. It defines how time and space connect. The faster you travel, the slower your time flows compared to someone at rest. At light speed, time stops entirely. For a photon, its entire journey, from star to eye, happens in an instant. Chapter 14. Why does the universe expand? Since the Big Bang, space itself has been stretching. Galaxies aren't flying through space. The space between them is growing. It's like raisins in rising bread dough. The more the dough expands, the further each raisin gets from the others. What drives it? Dark energy, perhaps, or something we don't yet understand. The universe isn't exploding outward. It's making more room inside itself. Chapter 15. Could time travel be real? Einstein's math says it's possible, in theory. If space and time are connected, twisting one could twist the other. A wormhole, if stable, might connect now and then. Traveling near a black hole could slow your time relative to others. But paradoxes lurk. What happens if you meet your past self? Maybe time protects itself. Maybe loops can't exist. Still, physics doesn't forbid time travel. It just makes it incredibly difficult. Chapter 16. How old is the universe? The universe is about 13.8 billion years old. We know this by tracing the light from the cosmic microwave background, the faint afterglow of the Big Bang. It's like the universe's baby photo, still whispering across the sky. Every star, every atom, every breath we take comes from that same beginning. The universe isn't ancient to itself. It's still growing, still changing, still writing its own future. Chapter 17. Are we made of stardust? Yes. The carbon in your skin, the calcium in your bones, the iron in your blood, all forged inside stars that lived, burned, and died long before Earth existed. Supernova scattered those elements into space, where new stars and planets formed. When you look at the night sky, you're seeing your own origins. We are not apart from the cosmos. We are its recycled light. Chapter 18. What is quantum entanglement? Two particles can become linked so tightly that changing one instantly affects the other, no matter the distance. Einstein called it spooky action at a distance. Yet, experiments prove it's real. Entangled particles share information faster than light, or perhaps outside time altogether. It suggests that space might not separate everything after all. The universe could be deeply connected in ways we're only starting to glimpse. Chapter 19. Could parallel universes exist? Quantum theory hints that every choice, every possibility, could create a new universe. In one, you turned left. In another, you didn't. These worlds might never meet, yet all could be real. Infinite versions of reality unfolding side by side. The multiverse isn't proven, but it explains the strange balance of physical laws. Maybe our universe is just one chapter in an endless cosmic library. Chapter 20. Why does space look black? Space seems dark because the universe isn't old enough for light to fill every corner. The stars we see are few among many, and their light hasn't reached us yet. Olber's paradox once asked, if there are infinite stars, why isn't the sky bright? The answer lies in time. The universe has a horizon, and beyond it, light is still on the way. The darkness isn't empty, it's unfinished. Chapter 21. What is the shape of the universe? The universe might be flat, curved, or something stranger. Scientists measure the cosmic background to see how light bends across space. So far, it seems flat, meaning parallel lines stay parallel forever. But if the universe is truly infinite, its shape could still curve beyond what we can see. Imagine trying to measure the surface of an ocean while standing on a single wave. That's how we see the cosmos. Chapter 22. What happens inside a star? Stars are nuclear engines. Deep inside, gravity crushes hydrogen so tightly that it fuses into helium, releasing light and heat. Every second, the sun converts millions of tons of mass into pure energy, enough to power life on Earth. Stars live, breathe, and die through fusion, balancing pressure and collapse. When the balance ends, they explode, scattering new elements, the universe's way of recycling matter into light. Chapter 23. Could time run backward? In physics, the laws work the same forward or backward. A ball rolling up a hill is just a reversed version of it rolling down. But entropy, the increase of disorder, gives time direction. If entropy ever decreased, time might appear to reverse. Theoretically, in a collapsing universe, time could flow backward. But for now, entropy only rises. That's why yesterday is memory, and tomorrow is possibility. Chapter 24. What is space-time? Space and time are not separate things. They're woven together into a single, four-dimensional fabric. Move fast through space, and you move slower through time. It's a cosmic trade-off. That's why astronauts age slightly slower than people on Earth. We all travel through space-time at the same ultimate speed, the speed of light, but we divide that journey differently between space and time. Chapter 25. Can space be bent? Yes. Massive objects like planets or stars bend the space-time around them. That's why light curves near the sun, and why galaxies distort the light from objects behind them. This bending is called gravitational lensing, and it lets us see galaxies billions of years old. Space is elastic. It stretches, twists, and warps like an invisible ocean. Gravity isn't pulling you down. Space is simply curving beneath your feet. Chapter 26. Is there a center of the universe? No. Every point in space is expanding away from every other. There's no center, no edge, just endless stretching. If you could rewind the universe, everything would collapse into one point, the Big Bang. But as it expands, every observer feels like they're at the center. It's not that the universe expands from somewhere. It expands everywhere equally. That's the strange democracy of the cosmos. Chapter 27. Could time end? If dark energy keeps accelerating the universe, galaxies will drift apart until stars die, atoms decay, and time itself loses meaning. It's called the heat death, a silent, frozen future where nothing changes. But if gravity wins again, the universe could collapse in a big crunch, resetting the clock. Either way, time may have boundaries. Every beginning might carry its own end, written quietly into physics. Chapter 28. How do we measure time in space? In orbit, astronauts use atomic clocks, devices so precise they lose only a second every million years. But even those need adjustment. Gravity and velocity shift time slightly, as Einstein predicted. GPS satellites correct for this constantly. Without relativity, your phone's location would drift kilometers off. Every moment you track on Earth is fine-tuned by physics happening far above it. Chapter 29. What is cosmic background radiation? It's the oldest light in the universe, a faint microwave glow from when atoms first formed, about 380,000 years after the Big Bang. Before that, the universe was a hot, opaque fog. As it cooled, light could finally travel freely, filling space with this soft afterglow. That radiation still surrounds us, a whisper from the universe's first dawn. Every photon in it is a message from the beginning of time. Chapter 30. Could the universe be a simulation? Some physicists think so. If reality runs on mathematical rules, could it be computed? If every particle behaves like information, perhaps we're inside a cosmic program. Yet, even if that's true, it doesn't change our experience. The equations are still real to us. Whether the universe is written in atoms or in code, the mystery remains the same. We're living inside something vast, and we're still trying to read it. Chapter 31. What happens at the edge of a black hole? At the event horizon, gravity becomes so strong that even light can't escape. Time slows almost to a stop, and space stretches infinitely. To an outside observer, anything falling in seems frozen, fading away forever. But from the inside, you'd cross the horizon without noticing. The laws of physics twist here. Matter collapses, and information hides. The edge of a black hole isn't a wall. It's a point of no return. Chapter 32. What is a neutron star? When a massive star dies but isn't heavy enough to form a black hole, it becomes a neutron star, a city-sized sphere of pure neutrons. Just a teaspoon of it would weigh billions of tons. It spins rapidly, sending beams of radiation into space like a cosmic lighthouse. Neutron stars are the densest objects in the universe that still have a surface. They are the halfway point between matter and collapse. Chapter 33. How do galaxies form? Galaxies begin as small clouds of gas drawn together by gravity. Over billions of years, they merge and grow, forming spirals, clusters, and giant ellipticals. At their centers often lie supermassive black holes, shaping how stars form. The Milky Way is one of hundreds of billions of galaxies, each with its own history of birth, collision, and rebirth. Galaxies aren't static islands, they're cosmic cities forever under construction. Chapter 34. What is the Milky Way? Our galaxy spans about 100,000 light-years and contains over 100 billion stars. We live in one of its spiral arms, orbiting the center every 230 million years. In the core lies Sagittarius A star, a supermassive black hole. From Earth, we see the Milky Way as a faint band across the sky, the glowing edge of our home's vast starry disk. It's both our address and our cosmic cradle. Chapter 35. How do stars die? Small stars like our sun fade into white dwarfs. Massive stars explode as supernovae, scattering their elements across space. The most massive collapse into black holes. Death in the cosmos isn't an ending, but a transformation. Every explosion seeds the next generation of stars and planets. The death of one star becomes the breath of countless worlds. Proof that destruction and creation share the same heartbeat. Chapter 36. Could we ever see the beginning of time? We can see. Chapter 37. What is a light year? A light year isn't time, it's distance. It's how far light travels in 1 year, about 9.46 trillion kilometers. When we say a star is 10 light years away, we mean its light took a decade to reach us. Every glance at the night sky is a look back in time. The farther you see, the older the story. Space is a museum of light, and every photon is a memory. Chapter 38. What is redshift? As the universe expands, light from distant galaxies. Chapter 39. What will happen to the Milky Way? In about 4 billion years, the Milky Way will collide with our neighbor, the Andromeda Galaxy. The two will merge, stars will scatter, and a new giant galaxy will form, likely named Milkomeda. Despite the drama, stars are so far apart that few will actually collide. From Earth's future sky, the view will be breathtaking. Two galaxies twisting together like a slow cosmic waltz. Chapter 40. Is the universe infinite? We don't know. The observable universe is finite, but beyond that, space might continue forever or loop back on itself. If it's infinite, there could be infinite versions of everything, repeating endlessly across eternity. But infinity isn't a number, it's a question. Maybe the universe doesn't end. Maybe it simply has no edges, like the surface of a sphere, curving back into itself forever. Chapter 41. What is the cosmic web? Across the universe, galaxies aren't scattered randomly. They form a vast, web-like structure, threads of light and gravity stretching billions of light years. Between them lie enormous voids, almost empty. The cosmic web is like the universe's skeleton, mapping how dark matter shaped everything we see. Each filament connects clusters of galaxies, glowing faintly with ancient starlight. The universe isn't chaos. It's an elegant pattern. Chapter 43. How do we know the universe is expanding? When astronomers looked at distant galaxies, they saw something strange. Their light was redshifted, stretched as if moving away. The farther a galaxy, the faster it recedes. That discovery, made by Edwin Hubble in 1929, changed everything. It meant the universe wasn't static, it was alive, growing. Every moment, space itself expands, carrying galaxies like driftwood on an invisible cosmic tide. Chapter 45. What is the multiverse theory? The multiverse idea says our universe might be one of many, each with different laws of physics. Some could have no stars, others no atoms. Quantum fluctuations during inflation may have spawned endless universes, like bubbles in a cosmic foam. We might never see them, but mathematics hints they could exist. If true, everything that can happen does happen, somewhere, sometime, in some universe. Chapter 46. What is a supernova? A supernova is a star's final, spectacular act. When its fuel runs out, gravity crushes its core, triggering an explosion that outshines entire galaxies. In seconds, it releases more energy than our sun will in its lifetime. Supernovae scatter heavy elements, gold, silver, oxygen, across space. They are cosmic forges, creating the building blocks of life. Every breath of air, every atom of iron began in one. Chapter 47. Could humans live on another planet? Maybe. Mars is our best candidate. Cold, dry, but reachable. It has water ice and day lengths similar to Earth's. Yet, survival there means mastering radiation, building habitats, and growing food in alien soil. Beyond Mars, moons like Europa and Titan may hold hidden oceans. Humanity's future might depend on learning not just to explore worlds, but to make them home. Chapter 48. What is a pulsar? A pulsar is a neutron star that spins rapidly, sending beams of radio waves from its magnetic poles. As it rotates, those beams sweep across space like a cosmic lighthouse. Some spin hundreds of times per second with perfect precision, better than atomic clocks. Pulsars help us measure cosmic distances, test relativity, and even detect gravitational waves. They are the ticking hearts of dead stars. Chapter 49. What are gravitational waves? When massive objects like black holes or neutron stars collide, they ripple space-time itself. These ripples, gravitational waves, travel across the cosmos, stretching and squeezing space as they go. First predicted by Einstein, they were finally detected in 2015. It was like hearing the universe for the first time. Now, we don't just see the cosmos, we can listen to it vibrate. Chapter 50. What happens inside a black hole? No one knows. Beyond the event horizon, space and time swap roles. Forward becomes inward, and every path leads to the singularity. Physics breaks down there. Equations stop working. Some theories say information is trapped on the surface, others that new universes could form within. Whatever lies inside, black holes remind us there are still places in the universe where knowledge ends and mystery begins. Chapter 51. What is the observable universe? The observable universe is everything we can see, limited by how far light has traveled since the Big Bang. It stretches about 46 billion light-years in every direction. Beyond that, light hasn't had time to reach us yet. What lies there, we can only imagine. The universe could continue endlessly, but our vision ends at the cosmic horizon, a bubble of light wrapped around all human knowledge. Chapter 52. Could the universe be older than we think? Maybe. Some galaxies appear more mature than they should be, given the universe's age. That puzzles scientists. Perhaps our models miss something, like early bursts of star formation or physics we don't yet understand. The light we see is ancient, stretched by time itself. So maybe the universe isn't older. Maybe time in its early days flowed differently, bending the way we measure age. Chapter 53. How do we know what stars are made of? Every element leaves a fingerprint in light. When starlight passes through a prism, it breaks into colors, a spectrum with dark lines where atoms absorb energy. By reading those lines, astronomers can tell what elements a star contains, how hot it burns, even how fast it moves. We've never touched the stars, yet through light alone, we've learned their chemistry, the language of the cosmos. Chapter 54. What is a supermassive black hole? At the center of most galaxies sits a monster, millions or even billions of times the sun's mass, compacted into a single point. These supermassive black holes shape the galaxies around them, controlling how stars form. They feed on dust and gas, releasing jets of energy that stretch across space. Despite their name, they might be the architects of order in the chaos of creation. Chapter 55. What is a quasar? A quasar is a galaxy powered by a feeding black hole. As matter falls in, it heats up, glowing brighter than entire galaxies. Quasars are beacons from the early universe, ancient lighthouses showing us how galaxies were born. Some shine so powerfully, their light travels billions of years to reach us, revealing the young cosmos when stars were just beginning to ignite. Chapter 56. Can space itself move? Yes, when galaxies drift apart. They're not moving through space. Space itself is expanding. Think of dots on a balloon as it inflates. They separate, not because they move, but because the surface grows. Space isn't static. It's dynamic, alive, and constantly stretching. Galaxies ride that flow like boats on a rising tide, carried by the invisible current of cosmic expansion. Chapter 59. What are cosmic rays? Cosmic rays are high-energy particles, mostly protons, that travel near the speed of light. They come from exploding stars, black holes, and distant galaxies. When they hit Earth's atmosphere, they create showers of smaller particles that rain down constantly. Every second, thousands pass through your body unnoticed. They are the universe's quiet messengers, carrying news from violent, unseen corners of space. Chapter 60. Why do we look up? Maybe because we came from there. The night sky is a mirror, showing us what we're made of and where we began. For all our science, curiosity remains our greatest force. Every question about space and time is really a question about ourselves, what we are, how we change, and why we exist. The cosmos doesn't just surround us, it lives within us. Chapter 61. What is dark matter made of? No one knows. It doesn't emit light or energy, but its gravity holds galaxies together. Without it, stars would scatter into space. Some say it's made of invisible particles, WIMPs or axions, that pass through us every second. Others think gravity itself may work differently on cosmic scales. Whatever it is, dark matter is the unseen hand shaping everything we see. Chapter 62. What is dark energy? Dark energy is even stranger. It's the force making the universe expand faster over time. Instead of pulling things together, like gravity, it pushes them apart. Scientists think it makes up nearly 70% of the cosmos. We don't know what it is, only that it's winning. Galaxies are racing away faster than ever, and someday, distant stars may fade beyond sight forever. Chapter 63. What is time dilation? Time slows down when you move fast or near strong gravity. To a traveler near a black hole, seconds feel normal, but years pass for someone far away. Astronauts experience tiny amounts of this on the ISS. It's not fiction, it's physics. Time isn't fixed, it bends and stretches with speed and mass. In Einstein's universe, clocks don't measure time. They measure motion through space-time. Chapter 64. What happens when stars die? Small stars fade quietly into white dwarfs. Bigger ones explode as supernovae, leaving behind neutron stars or black holes. Their ashes, carbon, oxygen, iron, spread through space, seeding new worlds. Death in the cosmos isn't the end, it's transformation. Every sunset, every heartbeat is made from the remains of stars that burned out billions of years ago. We are their legacy. Chapter 65. Could we ever time travel? In theory, yes, at least forward. Moving close to light speed would make time slow for you, while the rest of the universe ages quickly. Traveling backward, though, breaks causality, effect before cause. Wormholes might offer a shortcut, but they remain purely theoretical. Still, physics doesn't forbid time travel. It just hides the door, somewhere deep in the equations of space-time. Chapter 66. What is the edge of the universe? There isn't one. The universe has no edge, no center. It's more like the surface of a balloon expanding, endless yet finite. If you traveled far enough in one direction, you might loop back where you started, though the journey would take longer than the universe has existed. Space doesn't end. It curves, folds, and stretches beyond imagination. Chapter 67. How cold is space? Extremely. In the vast emptiness between galaxies, temperatures drop to about 2.7 Kelvin, just above absolute zero. That's the leftover glow from the Big Bang, a faint cosmic background bathing all of space. Yet in other regions, near stars or quasars, heat can soar to millions of degrees. Space isn't one temperature. It's a wild landscape of extremes. Chapter 68. Could life exist without light? Yes. Deep under Earth's oceans, creatures live near hydrothermal vents, thriving in total darkness, feeding on chemicals instead of sunlight. The same could happen beneath the icy crusts of moons like Europa or Enceladus. Life doesn't need sunshine. It needs energy, stability, and time. The universe is full of places that could quietly cradle life, unseen by any telescope. Chapter 69. What is quantum entanglement? When two particles become entangled, their states link instantly, no matter the distance. Change one, and the other responds, faster than light, yet without sending information. Einstein called it spooky action at a distance. It challenges our idea of space and time, hinting that reality might be more connected and less local than we ever imagined. Chapter 70. Could we ever see the beginning of time? Almost. The farthest light we can see, the cosmic microwave background, comes from about 380,000 years after the Big Bang. Before that, the universe was opaque, filled with plasma. We can't see through it, but we can sense its echo. Those faint microwaves are the universe's baby picture, the moment light first escaped, revealing where time itself began to flow. Chapter 71. What is a wormhole? A wormhole is a theoretical tunnel through space-time, a shortcut connecting two distant points. If real, one end could be near Earth and the other across the galaxy, but keeping it open would require exotic matter with negative energy, something we've never found. Wormholes exist in math, not in metal, yet they remind us that the universe might hold doors we're not ready to open. Chapter 72. Could the universe be a simulation? Some scientists and philosophers say it's possible. If advanced beings created a universe inside a computer, its inhabitants wouldn't know, just as characters in a game can't see the player. The rules of physics could be the program. Quantum randomness might be the code. Whether true or not, the question forces us to ask, If reality is simulated, what does that make consciousness? Chapter 73. What is spaghettification? Near a black hole, gravity changes so fast that your feet could feel much more pull than your head. You'd stretch out like spaghetti. That's spaghettification. It's the ultimate tidal force, ripping apart anything that gets too close. The process sounds terrifying, but it's also elegant. The final surrender of matter to gravity's pure geometry. Chapter 74. How do black holes evaporate? Stephen Hawking discovered that black holes aren't perfectly black. They emit faint radiation, tiny particles escaping from the edge of the event horizon. Over time, this radiation makes them lose mass. A massive black hole could take longer than the age of the universe to vanish. But eventually, even these cosmic giants fade, whispering their last energy back into the void. Chapter 75. What happens if two black holes collide? When two black holes merge, they dance first, spiraling closer, twisting space-time itself. Then they collide, fusing into one larger whole and releasing immense energy as gravitational waves. It's a silent explosion, invisible, yet powerful enough to shake the universe. For a moment, reality ripples, and space itself rings like a struck bell. Chapter 76. What is cosmic background radiation? It's the leftover glow from the Big Bang, now cooled to microwaves. Discovered accidentally in 1965, it fills the entire universe with a faint hum of energy. This light carries the story of the cosmos's first moments, tiny ripples that grew into galaxies and stars. It's the oldest light we'll ever see, a fossil of creation still echoing around us. Chapter 77. Could the universe end? Yes, in several ways. It might keep expanding forever until all stars die, leaving darkness. Point. Heat death. Or gravity could reverse the expansion, collapsing everything back into a big crunch. Some theories predict a big rip, where space itself tears apart. Whatever the end, the universe will change form, but its energy will remain. Nothing truly disappears. Chapter 78. What are parallel universes? In quantum theory, every decision might split reality. In one universe, you're reading this. In another, you never were. Each branch holds a version of events, all existing simultaneously. These parallel universes can't communicate, yet they might explain quantum uncertainty. If true, infinity isn't out there. It's everywhere, layered over itself like pages in an endless book. Chapter 79. What is cosmic dust? Cosmic dust sounds small, but it builds everything. These grains, made from dying stars, float through galaxies, forming clouds that birth new suns and planets. Every world, every living thing begins as dust. Even now, billions of these ancient particles drift through Earth's atmosphere, tiny fragments of the universe silently falling into our lives. Chapter 80. Could humans become immortal through space? Not biologically, but maybe cosmically. If humanity spreads across planets and stars, our ideas, art, and DNA could outlive Earth. In the long run, survival might mean evolution. Chapter 81. What is antimatter? Antimatter is the mirror opposite of matter. For every particle, there's an antiparticle. Same mass, opposite charge. When the two meet, they annihilate into pure energy. In the early universe, matter and antimatter should have canceled each other out. Yet somehow, a tiny imbalance left everything that exists. That small flaw in symmetry is why stars shine, planets form, and we're here at all. Chapter 82. Could we harness antimatter? In theory, yes. It's the most powerful fuel imaginable. A gram of antimatter could release as much energy as a nuclear bomb. But creating and storing it is nearly impossible. It destroys anything it touches. Scientists have made only tiny amounts in labs. If we ever master it, antimatter could power interstellar travel or end civilization in a spark. Chapter 83. What is the speed of light, Linnet? Light speed, 299,792 kilometers per second, is the universe's shrinking the distance between 2 points. You wouldn't move faster than light, you'd move less. It's an idea based on Einstein's equations, but it requires exotic energy we don't have. Still, it proves something profound. Physics doesn't forbid dreaming big, only demands precision. Chapter 85. What is relativity? Einstein's theory showed that space and time are one fabric, warped by mass and motion. Gravity isn't a force pulling objects. It's the curvature of space-time itself. Planets orbit stars because they follow the shape of that curve. Relativity changed how we see everything, from GPS satellites to the expansion of the universe. It's not just science, it's the geometry of reality. Chapter 86. How big is the universe? At least 93 billion light-years across. That's just the observable part. Beyond it, there could be infinite space, full of galaxies we'll never see. The more we look, the bigger it gets. The scale defies imagination. Billions of galaxies, each with billions of stars, each star possibly with worlds. The universe isn't just vast, it's overwhelming and humbling. Chapter 87. What is a neutron star? A neutron star is the crushed core of a giant star, smaller than a city, but heavier than the sun. A teaspoon of its matter weighs billions of tons. Its gravity bends light. Its magnetic fields tear atoms apart. Yet it spins with perfect rhythm, like a cosmic clock. Its death turned into precision, the heartbeat of a collapsed universe. Chapter 88. Could the universe think? Some philosophers suggest consciousness might be fundamental, not just a product of the brain, but woven into the fabric of reality. The universe observes itself through us, perhaps through countless beings elsewhere. Maybe intelligence isn't rare. Maybe it's inevitable, like stars. If so, thought is just the cosmos learning to recognize its own reflection. Chapter 89. What is the Great Filter? It's the mystery of why we haven't found other intelligent life. Somewhere between life's beginning and galactic civilization lies a barrier, a step most fail to cross. It could be rare biology, self-destruction, or cosmic catastrophe. Maybe we passed it. Maybe it's still ahead. The silence of the stars could be warning or invitation. Chapter 90. Could quietest corners of space, quantum fluctuations hum. The universe never truly rests. Time, like breath, is the pulse that keeps existence alive. Chapter 91. What is quantum foam? At the smallest scales, space-time isn't smooth. It flickers and bubbles like foam. Tiny fluctuations constantly appear and vanish, bending reality itself. This quantum foam might be the foundation of everything, the texture from which space, time, and matter emerge. It's chaos at the smallest level, Yet from it rises the elegant order of galaxies and stars. Chapter 92. Could black holes create universes? Some theories suggest every black hole might spawn a new universe inside its singularity. What looks like destruction from our side could be creation on another. Each universe could inherit its parents' physical laws, evolving like a cosmic family tree. If true, we might be living inside one, the child of a dying star from another reality. Chapter 93. What is the heat death of the universe? In the far future, all stars will burn out, galaxies drift apart, and black holes evaporate. Energy will spread evenly, leaving no difference between one place and another. No motion, no light, no life. It's called heat death, the universe at perfect balance and complete stillness. Not fire, but silence. An ending colder than imagination. Chapter 94. Could consciousness survive the end of the universe? Maybe, but not in human form. If intelligence merges with machines or energy, it could adapt, spread, and evolve beyond biology. Some physicists even imagine minds encoded into quantum fields or patterns in space-time. Consciousness might not be tied to matter. It could be a process the universe itself keeps replaying again and again. Chapter 95. What is the arrow of time? Time flows forward because entropy, disorder, always increases. A broken cup doesn't unbreak. Smoke doesn't return to fire. The arrow of time points from order to chaos, powered by the universe's tendency to spread energy evenly. It's why we remember the past, but not the future, because the universe itself remembers which way it's moving. Chapter 96. Could we ever control gravity? Gravity is the weakest force, yet it shapes everything. If we could manipulate it, we could lift cities, warp time, or travel the stars. Some experiments with superconductors and quantum fields hint it might be possible someday. But for now, gravity remains untamed, the universe's oldest secret, quietly holding everything together. Chapter 97. What is the shape of the universe? It might be flat, curved, or saddle-shaped. Current data suggests it's almost perfectly flat, meaning parallel lines never meet, and geometry behaves normally on cosmic scales. But we can't be certain. The universe could be finite yet unbounded, looping back on itself like a sphere in higher dimensions. Its shape defines not just space, but destiny. Chapter 98. Could the universe be conscious? Some scientists wonder if consciousness emerges from complexity, and the universe is the ultimate complexity. Galaxies connect like neural networks. Energy flows like thought. Maybe awareness isn't local. Maybe it's universal. We might be neurons in a vast cosmic mind, each act of observation lighting another spark in the universe's endless self-awareness. Chapter 99. What lies beyond the universe? Nothing or everything. Beyond the cosmic horizon may be other universes, realms with new laws of physics, or endless repetition of our own. But by definition, beyond lies outside space and time, concepts we can't reach. The universe might not be inside anything. It might simply be all that ever was, is, and could be. Chapter 100. Why do we ask these questions? Because wonder is the universe speaking through us. We look up not for answers, but for connection, to remember we're part of something vast and alive. Every question about space and time is a reflection of ourselves, seeking meaning in the infinite. The cosmos began in silence, But through our curiosity, it has finally found its voice. As the last question fades, let your thoughts drift like starlight through the dark. You've traveled across galaxies, touched the edges of time, and found silence waiting at the center of everything. Remember, the same particles that built the stars are still burning quietly inside you. You are not small in the universe. You are part of it. So close your eyes, breathe deep, and let the universe keep talking while you rest. Because even in sleep, you're still listening to the story of everything. Good night, traveler of stars. See you in the next story.